Okay, so I guess we haven't had done this in a little while, so I might have to review a few things. But what I want to continue on the kinds of thing that Gauss was looking at in his work on the arithmetic geometric mean and the elliptical functions. But I want to look at it from the standpoint of the idea that Lin has been emphasizing of a finite but self-bounded universe. And this really takes a little bit of effort to get a sense of this for a couple of reasons. First of all, what Gauss developed on this was it was fragmentary. Right? Some of Riemann's work is less fragmentary on it, but nevertheless, even if it were more developed, the problem is neither one of them states explicitly the epistemological significance of these ideas, which Lin emphasizes. And so we have to look at this from that more advanced standpoint. Now, and I guess one takeoff point is the thing that Lin was emphasizing in one of the more recent papers, where he talked about with Kepler's discovery of the planetary orbits that it was necessary to replace the idea of an ellipse as a conic section and instead understand the ellipse as from a higher standpoint. And this also gets to this question of what really is spherics, because there's a tendency, which is a wrong one, to think that spherics means spheres, and it doesn't. It means a method of physical geometry. Basically, it's a method of anti-Euclidean physical geometry. Now, and this is explicitly stated in the Timaeus dialogue, where Timaeus gives the disclaimer that all intelligent people always give when they're discussing science, is they say, okay, I'm going to have to use these words and images to communicate the idea, but don't mistake the words and images for the idea. And so when Timaeus describes the spherical nature of the universe, he's using the image of a sphere as the image of something that is finite but self-bounded, as Einstein would say. But there's a aspect to that which is not really, which takes us outside the sphere, which is already implied by the Archytas construction, and is also mentioned in the Timaeus dialogue, where Plato makes this comment that if God had made the world flat, all you would need was one mean between two extremes, but since he made it solid, you always need two. Now, the reason why that's significant from this, the connection between that and this idea of what spherics is that when you look at the idea of the so-called flat world, you have the idea of one mean between two extremes. But let me just point out, when Plato mentioned flat, he didn't mean what Euclid meant as flat. Because a Euclidean space, a flat space, has a certain, as Gauss pointed out, has a certain characteristic curvature, and there's no defining characteristics to it. It's this fantasy world imagined by assuming by starting with the definition of a point, line, surface, and so forth, right? Whereas when Plato means flat, what he means is basically the difference between circular and spherical.
Because the surface of a sphere is flat.
No. I don't think Plato had that idea, but I think what he means by the difference between flat and spherical is the difference between circular action and spherical action. Yeah, well, it's very simple, right? Because in order to construct one mean between two extremes, right, you do that by the motion of a circle, of a point, a right angle in a circle. So what you're really looking at, which Plato doesn't emphasize, but what Kuza later does, is that the one mean between two extremes is in effect a function of the relationship of the curve to the straight, because you have the vertex of the right angle moving on a circle and the perpendicular moving along a line. And those two motions are non-uniform with respect to each other, right? And if you make the motion along the circle uniform, the motion along the line will be non-uniform. If you make the motion along the line uniform, the motion along the circle will be non-uniform. So you can't make those two things commensurable. They're two different types of actions. Now, that expresses itself in the doubling of the square with respect to the incommensurability of this diagonal to the side. That if you have two squares whose ratios are in a certain proportion, their areas will, whose areas are in a rational proportion, their sides will not be. Right? So that, even though that's a relationship which deals strictly with lines, or in the domain that Leibniz would later call algebraic, it's actually a special case of this more general type of function, which Kuza discusses as the quantities associated with the curved and the straight, the comparison of the curved and the straight. And that's where one mean between two extremes comes from. In other words, it doesn't come out of a Euclidean space. It comes only out of circular action. The circle in that, but Plato says that God didn't make the world flat. He made it solid. So we have to have two means between two extremes. And as the Archytas construction shows, in order to make two means between two extremes, you have to have an action which is not spherical. But it's the action of moving a circle around a point so that you end up with a double circular action. So now instead of having the curve, the point, I didn't bring the animation, but the point Q that's moving on the line in the circular construction is also moving on the line, but it's moving on the circle as well. And then the point P is moving on a circle, and it's moving on the intersection between the torus and the cylinder. So from Kuza's standpoint, the Archytas construction is a different type of quantity. And that type of quantity is a quantity associated not simply with the curved and the straight, but two different types of curvature with the straight. So it's a double curvature, two things interacting together, two different types of curves interacting together generates that quantity. And that's non-spherical. Now, from Riemann and Gauss's standpoint, that such an action would be called elliptical. So in a certain sense, you could say that the doubling of the square comes from a spherical action, but the doubling of the cube comes from an elliptical action. And what we mean by elliptical here is not an ellipse. What we mean by elliptical is the functional relationship which produces the ellipse. So what we're looking at is to try and get the most general concept that produces these particular results, which is what Theaetetus is arguing, right? When Theaetetus is doing, he's saying, okay, yeah, you can double the square, triple it, quadruple it, etc., but what's the general principle? And if you have the general principle, all the specifics come together. So it doesn't matter whether you're doubling, tripling, quadrupling, or making two squares whose areas are in the proportion 3 to 2, or 5 to 7, or 99 to 101. You're still generating magnitudes that are a function of this relationship of the curve to the straight. That's the functional relationship which generates that. And so you can look at this geometrical construction of the Greeks from the advanced standpoint of Leibniz, Gauss, and Riemann, and recognizing there this concept that they called, that Leibniz and Gauss and Riemann particularly understood as a function. And now it's usually, I often recoil when you see these treatments of Greek geometry that where they say, okay, we're going to look at this from the modern standpoint, and they write out an algebraic equation to describe the doubling of the cube or something like that. But there is a benefit, not in that way, but looking at it from a modern standpoint, to really understanding how this, to look at the to look at it from the standpoint of Gauss and Riemann. So in a certain sense, Plato really didn't have the same conception that Leibniz, Gauss, and Riemann had of a function, but in a sense they did. Because, in other words, they looked at the square as being the effect which is produced by this idea of one mean between two extremes. So when you speak of square magnitudes, you're not really talking about squares. You're talking about the fact that squares are visible objects which exist, which are the effect of a type of action whose boundary conditions are associated with the motion of this curve to the straight. Whereas the cubic magnitudes require a higher a higher set of boundary conditions. Okay, and that's a higher type of function.
So you said that at first you said that the flat is
Circular.
Circular, and then you said that it's actually spherical.
Yeah, because a circle is a sphere.
Right.
It exists in a spherical domain, whereas an ellipse,
Okay.
as when you look at it from the standpoint of Gauss and Riemann, is not a spherical. It's outside the sphere. It's a higher type of geometry. So, from the standpoint of this idea of finite but self-bounded,
Why is this?
huh?
Why is this?
What is what?
Why the ellipse is the higher domain of the space?
Because the ellipse, in order to an elliptical function is created. An ellipse is created by has a function which is two incommensurables, two actions acting together to produce the elliptical motion, which is not spherical. Right?
It describes, would you say it describes the relationship between two of those spherical functions? A relationship between two of the spherical
No, it's not spherical functions. It's something completely different.
And you wouldn't call it the relationship
No.
between?
No.
Okay.
Like if you take the ellipse, right, and you take the elliptical function, this sign here, look at the relationship of this sign to this one. Okay? And the relationship is an interesting one because in the case of the circle, the circular sign is incommensurable with the angle and it's incommensurable with the arc. But since the arc and the angle are commensurable, the sign has only one type of curved action, which it's in between.
The sign is incommensurable with which angle?
Any angle. But in this angle E, which is this angle here. Okay. The angle that the white line makes. Okay? But the sign, the elliptical sign, is incommensurable with that angle, but it's also incommensurable with the arc of the ellipse in a different way. So it's a function of two principles acting together, the curved and the curved. So it's not just the curved and the straight, but it's two different types of curvature interacting together to produce this elliptical effect. That's what's called an elliptical function.
When you say that you describe the square as the interaction between the straight and the curve.
Yeah, because it's just one mean between two extremes.
Where's the curve in this?
right angle inscribed in a circle. That's how you get all possible means between one mean between two extremes. Right, the thing with the, you remember that? Right angle in the circle? Stephanie?
Yeah.
No, I don't understand what you're saying. I see a right angle in a circle and somehow see a square, but I don't.
When you have a right angle in a circle, right? And we call these. Then OP is the geometric mean between OQ and OA, among other types of relationships in there.
All possible.
So all possible relationships. In other words, think of the square as being one geometric mean between two extremes. Instead of thinking of the square, and then you draw the diagonal, and you say, okay, one mean between two extremes comes from the squares, invert that. And say the squares come from the function which generates one mean between two extremes. That function has a certain geometrical characteristic. And that geometrical characteristic is this characteristic of this incommensurability between the action along a circle and action along a line that are united together. They're acting as a united effort. But when you deal with the two means between two extremes, you have to put two types of curvature in there. And that two types of curvature are required to get two means between two extremes. So there's a different function which generates cubic magnitudes. And the cubic magnitudes, and those types of functions are called, in the domain of Gauss and Riemann and so forth, since that time, elliptical functions. The name elliptical is attached to them because their discovery arose out of the investigation of the ellipse, elliptical orbits of Kepler. But once they were discovered, it became clear that a whole class of functions were actually elliptical functions, which hadn't previously had any identification with the ellipse at all, like the Architas construction. You know, you wouldn't associate the Architas construction with an elliptical function. But
And the Greeks didn't.
no, the Greeks' conception of the ellipse was as a conic section.
Right.
But when you look at when you look at the ellipse as from the standpoint of astrodynamics, then you see that there's something else there, which is a higher principle. Now, the step between the Greeks and Kepler and the elliptical functions is Leibniz's calculus and Leibniz's discovery of the Catenary Principle. Because Leibniz's discovery of the Catenary Principle identifies something quite interesting in this regard, which is that here you have a physical principle, a hanging chain, which hangs in the shape of the catenary. And there's, you can change the hanging points, you can change the characteristics of the chain, you can do anything you want, but the chain always moves in a catenary curve. There's a single pathway which is defined. That pathway is defined, that catenary pathway, Leibniz shows, is defined because the characteristic curvature of what Riemann would call manifold, in which it exists, is determined by the arithmetic mean between these two exponential curves. So that defines a certain characteristic. Now, the reason why that's a link is that first look at this question of the Greeks, right, with the idea of one geometric mean between two extremes. First you look at just the line, which is the kind of relationships that the Greeks called arithmetic. Then you have the one geometric mean between two extremes, which they call geometric. Geometric, a function which is characterized by geometric action. They call it geometric. Then you have two geometric means, three geometric means. All that was understood under the general idea that Leibniz called algebraic magnitudes. But there's a higher type of magnitude over and above the simple geometric, which is what Leibniz called transcendental. right? In a certain sense, you could also not inaccurately say that the simple transcendental functions, these exponential functions, are in a sense hypergeometric, because they're not really geometric. It doesn't really define a geometric action of a particular number of geometric means between two extremes. It defines all possible numbers of geometric means between two extremes, right? In other words, if you take this action here, produces the possibility of creating one mean between two extremes, but it can never produce two. To produce two, you have to do something like the Architas construction. So that's a different type of action. So, and that produces all possible two geometric means between two extremes, but it doesn't produce four. Now, the exponential type of functions, the so-called logarithmic exponential functions, which were not really discovered until Leibniz. He's the one who really invented this. Why Lynn often refers to the two things was Leibniz's Catenary Principle and discovery of natural logarithms. Because his discovery of the principle, the so-called logarithmic exponential principle as a function, he didn't discover logarithms, that was discovered by Napier, but discovered as a function, what Leibniz is really showing is that there's a higher type of function from which all possible algebraic functions could be generated. Two means between two extremes, 3, 4, 7 million, etc. That's why Leibniz says this ends the use of algebra for physics, because when you look at physical processes, they're characterized by, like the catenary, by these types of functions, which are not simply one mean between two extremes or two means between two extremes, but by what Leibniz called a transcendental action. Okay? So
Leibniz doesn't call this elliptical, I mean, he doesn't have it.
no, Leibniz didn't have the elliptical functions. That comes with Gauss. But Leibniz was looking at, Leibniz was close to getting this idea of the elliptical function, because he was already looking at the fact that you have this, when you have he was looking at the way these different functions interact, these higher functions interact with each other. So for example, if you take the line, the arithmetic relationship, those are the relationships associated with the line. If you have the geometric relationships,
Arithmetic means basically increasing in a constant, growing or increasing in a completely constant way.
yeah, the arithmetic relationship is when things and everything is constant. The intervals are the same and the differences between them are the same. Okay, the geometric, the way the Greeks talked about it, is that the intervals are different, but the proportions are always the same. Okay, and so if I have a square and I double it and I triple it, then you have the powers increase arithmetically, and the effect increases geometrically. Right? That's the idea, right? In other words, 0, 1, 2, then you do it again, 3, right? So geometric, what corresponds to geometric increases in effect, right, produce or correspond to arithmetic increases in power. Right?
So
yeah.
what you draw over there?
The Theaetetus thing with a square, and then I doubled the square, and then I quadrupled, then I doubled that, and then doubled that. But the proportions are always the same, because the differences are different. The difference between 0 and 1 is 1. The difference between 1 and 2, between 2 and 4 is 2, right? So the differences are different, but the proportions are always the same. Right? So you see how even when you get into the geometric construction, that the arithmetic is still there, right? It's there, but it's incorporated into a higher principle. Now, what Leibniz was looking at is, well, and this, of course, is generalized in the idea of the exponential function, that Leibniz's idea of an exponential function, in which arithmetic, where the way he describes the exponential function is the relationship between the arithmetic and the geometric. These arithmetic changes in one direction correspond to geometric changes in the other direction. So it's the general case of this relationship of the arithmetic to the geometric. And you still have this same relationship that if you take any arithmetic relationship on the horizontal, it corresponds to geometric relationship in the vertical. So the arithmetic and the geometric are combined together in this transcendental domain.
That's still, though, it's interesting, that still has some relationship to the curve on the straight.
Yes.
Because,
Yeah.
because the illusion of the demonstration is that each point along the way
Right.
is a definite straight
Exactly.
And then the
generation.
catenary is.
But the catenary is
relationship-
not. The
That's right.
catenary is curved.
The catenary is curved in a different way.
It's
And
completely
it's the
different.
relationship between those.
Yeah. Now,
Still an arithmetic mean.
yeah, the arithmetic mean between these two. Now, here's the thing that Leibniz was looking at. Well, what about a function in which the proportions are changing exponentially? Like here in the arithmetic, the proportion, the
The rate of change is constant.
no, forget that. The difference is the proportion is the same. That is, 1 is double, 2 is double 1, 4 is double 2. This is always 2. That's what doesn't change, right? Okay. But Leibniz was looking at, and haven't got the original paper. The only reference I have to it is in a secondary work referring to Gauss's work on this. But Leibniz already in the Bernoullis were looking at a function in which instead of the powers increasing arithmetically, okay, the powers increase by the square. Okay, so those are basically your biquadratics, right? So you take out, right? You just get your squares, right? So the way this would work out, the way this would look as a series, would be 1 x to the 4th, x to the 9th, x to the 16th, right? You see where the x to the 25th, right? So the powers go up by the square. Okay? So if the powers go up by the square, then the proportions are changing exponentially. So the proportion between 1 and x is x. The proportion between x and x to the 4th is x cubed. The proportion between x to the 4th and x to the 9th is x to the 5th. The proportion between x to the 9th and x to the 16th is x to the 7th. So you get your x to the 11th, your odd number. So you see how the proportions are increasing geometrically, right? That's what this is really the first.
9, x to the 9.
Yeah,
I'm sorry. This is the first example of what Gauss would later call a hypergeometric action. Because if you think of the geometric being characterizing equal proportionality, the hypergeometric is when the proportionality itself is increasing exponentially. Okay? And this type of function, the only reference I have is that Leibniz was looking at it with respect to probability theory. But there may be more involved in it. Gauss investigated this with respect to the elliptical functions and the arithmetic geometric mean. These are the functions that I talked about in the what he called P and Q. These what Jacobi later called theta functions, right? And you can define two types of these. One is a theta function, which would be in one direction, and the other would be which is where you have, that's in the other direction.
Those all minuses or
Every other one, right? In other words, if you I'm sorry, every other one, right? So you have two functions, and that's exactly the same as e to the x and e to the minus x. One, e to the x would have all the powers positive, and e to the minus x would have all the positive, all the even powers be positive, because a minus times a minus is going to equal plus. But all the odd powers, since it's a minus times a minus times a minus, would be negative, right? So that's just this. You can't draw a picture of these two things going that way. Two different. No, you can't, because visible space doesn't give you the option of doing that.
because they move too fast.
Because there are too many directions. There are 4 directions involved, and you only have 3 in visible space. Because if you think of e to the x and e to the minus x, right? This one is a spiral this way, and the other is a spiral that way. Remember, I did that one. And the only way you can have a space which has those two things, your left hand and your right hand, is if you rotate them that way. You can't do anything in this plane, move them together. So you got to rotate them this way. So that already takes up all of visible space. So now you got to think of something which rotates, which has 4 different branches, right? You can see the footprints of it. You can in the complex domain, but you can't. Okay. Now these functions, then, what Gauss shows are what defines the elliptical functions. That just as the catenary curve is 2 geometric means, is the arithmetic mean between 2 exponential functions, the elliptical function are not the arithmetic mean, but the proportion of these two together, right? And as he shows, the relationship of these two things is not with respect to the arithmetic mean or the geometric mean, but this arithmetic geometric mean relationship to it. Now, yeah.
How to illustrate that in invisible space, but can't use force?
No.
No.
Yeah, you could, but you have to.
But that's a footprint.
Yeah, you have to make certain
Shadow
assumptions.
of it.
All right, now, so that's the direction that Gauss is looking at on this. This is where Gauss's thinking is coming from on this question of the hypergeometric. In other words, if you think about it from the standpoint of spherics, he's looking at how the geometric, you have the arithmetic, then you have the geometric, then you have the geometric as being the effect of the combining, also including the arithmetic, in which the proportions now are, in a certain sense, the proportions are equal. But then when the proportions themselves grow exponentially, now you're into what he called the hypergeometric. Okay? And it's in that hypergeometric domain that the elliptical function is actually taking place. It's in the domain in which the relationship between, because you have two incommensurable actions. Now, we've given, another way to get a handle on this is to look at it from 2 other examples. One I already gave, we worked on a long time ago. Yeah, this one is the pendulum, right? Where you can see that you have, because the pendulum is accelerating, you have an incommensurability between the rate at which the sine, the blue line is just the sine changing with respect to the angle, and the red sine is the sine that is actually how the sine is changing with respect to the accelerating motion of the pendulum.
So you change the pendulum to an orbit.
Yeah, because I wanted to because when you do it small swings of the pendulum, this is where Galileo was a faker. If you have small swings of the pendulum, you can approximate the motion of the pendulum by the sine of the angle. But when you have a large swing of the pendulum, then it's not simply the sine of the angle. It's a function both of the sine of the angle and the acceleration due to gravity, right? Which is what I'm showing there, how the two are incommensurable. Now, so what you have, the ironic thing is that a circular pendulum, and here we have the cycloidal one, and the cycloidal one sort of finds the mean between those two incommensurables. So the cycloidal pendulum is actually existing in a circular or spherical phase space, whereas a circular pendulum is in an elliptical one. Now, another example of this, which I didn't bring because I didn't really have a way to do it. The circular pendulum is
Trying
in...
to see it.
Oh, yeah. Okay, now, now here's the funny thing. Another example of this is a top, which I didn't bring. I have one that they gave me in Boston.
Gyroscopic top.
Well, just any top, right? But anyway, I have this one that spins pretty nicely, but I didn't bring it because I didn't have any place to spin it on. I didn't want to spin it on the piano. But this is also what the precession of the equinox, the Earth's precession is, because when you have a top, you have the top is spinning on its axis, but it's spinning on its axis not in absolute space. It's spinning on its axis with respect to the gravitational potential of the Earth. Right? So while it's spinning, it's also reacting to the gravitational potential of the Earth, which causes the axis around which it's spinning to also rotate.
So what is the Earth relating to the gravitational pull if the top is relating to the gravitational pull of the
Well, the Earth is rotating in the solar system and the galaxy and everything else.
So it's
But the top
not
is...
some kind of...
But the effect of the sun's, the effect of the sun on the top is relatively minor compared to the Earth on the top. So we can disregard that for the moment.
But it's the sun on the Earth?
No. No. On the Earth's precession?
Yeah.
Oh no, the Earth's precession also involves Jupiter. Has to do with Jupiter as well as the sun. But just take this simple case of the top, right? The top. So the top has it rotates around its axis, and it rotates around its, and it also precesses. Now Jacobi and Riemann looked at this and understood that this was an example of an elliptical function. That actually the top's motion was in effect elliptical because it was two periodic actions interacting together. Now this idea, so in other words, it's the same type of quantity that an elliptical functions quantity is a quantity of the periodic effect of the curved and a curved. And now, and this is an interesting story, which is quite funny because this is the way Riemann and Jacobi, and just like Leibniz, recognized that the catenary's relationship to the exponential expressed a fundamental characteristic about the nature of physical space-time, Jacobi and Riemann recognized that the spinning top, or the motion of the Earth, was the effect, was not moving in absolute, it was not occurring in absolute space. It was occurring in an elliptical phase space. Now, Felix Klein and Arnold Sommerfeld wrote a 674-page book on the motion of the spinning top.
You'll explain?
Yeah.
Can you write his name?
Huh? Felix Klein, K-L-E-I.
My spelling.
Klein and Arnold Sommerfeld. Arnold Sommerfeld was the physicist in Munich who had developed the hypothesis that the electron orbits were elliptical, to try and correct some of the problems in Bohr. In any case, it's very interesting because Klein also came, I think, to Princeton. Or I think it was Princeton, not Columbia. I think it was Princeton, where he gave a series of lectures on his mathematics of the spinning top to show that it mathematically could be treated as an elliptical function. I didn't bring the quote with me, but what Klein, but however, you see the sophistry here, because what Klein says is, okay, you can look at the spinning top, and you can measure its motion, and you can describe its motion like in a Cartesian coordinate system, where you have an XYZ axis around which it's spinning. So that's 3 coordinates. And then you have, on the spinning on its axis, the X and Y coordinates would be changing, but the Z coordinate wouldn't be. But then you have 3 other coordinates, X prime, Y prime, Z prime, around which the XYZ axis, right? Or you could do the same thing, make the same mathematical description by expressing the motion of the top based on 3 angles, so-called Euler angles, yaw, pitch, and roll. This angle, and that angle, right? The 3 angles in space, right? So you can make a function like that. Or, he says, you can treat it like, in the complex domain, like a elliptical function. And then he shows you how you do that. And then he says, however, so you can treat the top as if its motion is actually occurring in non-Euclidean geometry. But the non-Euclidean geometry here is purely a matter of convenience.
Oh.
We're not saying that the top actually is moving in non-Euclidean space. The use of non-Euclidean geometry is purely for mathematical efficiency.
Just like Euler, huh?
Yeah. So, but this is the role Klein
Before you
played.
change that, can I ask a question?
Yeah.
Because
Yeah.
I'm trying to figure out this one.
Geometry other than
Yeah.
No, well, I think you said that what's happening in this spinning
Yeah.
thing is not commensurate with the sign.
Yeah, the blue line is the sign moving, is the way in which the sign changes with respect to the angle.
So, but it's a periodicity of the sign, because it's the same lengths as the sign,
Yeah.
right?
Right.
So they're in different periodicity.
There are
because
2
of-
period. That's right. There's an additional thing which is acting on the sign's periodicity to make it increase and decrease at a different rate than it would if it were
Because of
just
gravity.
being dependent on an angle.
Okay.
Exactly, right? And that's the same thing you get with this spinning top. You have the motion of the top spinning, but since it's spinning in gravitational potential, you have the effect of that gravitational potential over the top, right? And that produces so there are 2 cycles acting together to produce that.
And you're saying Galileo denied that? That
Galileo said that
periodicity
the
was
circular
same?
pendulum was isochronic. It was equal time, right? Because he did it by looking at the chandelier swinging in church, and he was bored, so he took his pulse and so
It's like the apple falling on your head.
that's the story.
But wouldn't the top be a kind of action motion very similar to the least time function?
Sure, all these things are
It
least.
seems to have a similar
Yeah. Absolutely. All these things, what you're looking at is think about it also from the standpoint of Kusa, which is also kind of fun that Kusa used the top as for a metaphor for the idea of the universe, not the sphere. He used the top, but the motion of a spinning top expresses also in the unfolded way the motion of this planetary motion. Now, I mean this idea of elliptical function. Now, so what you have is the idea of one universe, but within that one universe you have a unfolding of physical actions which increase whose power increases with the number of actions that are occurring to produce that effect. Now, one of Riemann's students introduced the idea of a tensor to describe this kind of quantity. A tensor is simply a type of quantity, which is a single quantity made up that's whose components are 3, 4, 5 x number of parameters that are interacting with each other. So in a certain sense, a simple function is a simple type of tensor. Now, so what Gauss was looking at, then you look at this from the other angle. The other direction is, well, how do you what's a type of function that from which we can express the relationships of these whole classes of functions, like the way the circle with the right angle expresses the one mean between two extremes, the Architas construction too, etc., etc. Okay. And that led Gauss to define what he called the elliptical modular functions. And these elliptical modular functions are a special case of a type of function which are called modular functions. And the elliptical modular is a special case. Now to understand these functions, let's look at it from from another standpoint that Gauss actually looked at it. Well, one way, before I get to that, okay. All right, now, one way to look at it is this way, right? One way to get at this is to think about this thing that you get with the cross ratio.
This is the tallest one?
Huh?
This is the tallest one?
No. No. This is Desargues' idea of the cross ratio, right? That you have this preservation of the cross ratio, right? When you project 4 points onto any other 4 points, right? You get the distance, the lengths between the 4 points change, and the proportions between the lengths change, but the proportions between the proportions stay the same. Okay? And that's why, when you see projective relationships, things appear to be in proportion to each other. They're not. What's in proportion to each other is the proportions. Right? And this, yeah. Now, this, now these proportions, so this is the same thing you get with the, remember the famous complete quadrilateral. Here's my picture of the complete quadrilateral. Okay. Right, so if you have a complete quadrilateral and you extend the sides and the diagonals till they all meet on the same line, then these points, make that B, make this D. These points,
What did you?
I drew a complete quadrilateral.
Okay.
Okay, so these points are all in what's called harmonic proportion, and the harmonic proportion is when the cross ratio equals -1. Now, but the point is that no matter how you change the shape of this complete quadrilateral, if these two sides become more parallel so that the diagonal goes off that way, then C changes its place. D moves further and further that way. C moves here. A and B will move, but they'll all stay in the same harmonic proportion. And then when these things become parallel, D will be, will be at infinity. And then when they move a little bit this way, D comes back that way. So this idea of the preservation of the cross ratio, when you look at it from that standpoint, reflects a spherical type bounding of the physical universe. Okay? And that spherical, that characteristic of the preservation of the cross ratio is also a characteristic of the complex domain. So that if you have, for example, here I did this. This is I have 4 points here on a sphere. You can see the red one's at 0, the black one's at infinity. This one is at 1, and this green one is at some other point, right? So that's very much. This is basically a complex version of the complete quadrilateral. So. And then if I
Where is D?
D would be the green one. Okay. Now if I put this through a series of certain transformations. Okay. So what I actually here I have these. This is my sphere. I have these 4 points on the sphere, and under this transformation, these 4 points end up there. Okay. Now the other thing you see about the sphere is that
What transformation?
it's just
On a
a
great circle?
simple Mobius transformation. Yeah, they're on a great circle, which
Second one.
yeah. So I have 4 points, John, on a circle.
A
That's
circle or on a sphere?
A circle on
a
a
circle on a sphere,
Ah.
and then they get mapped to a great circle on the sphere, where one of them goes to 0, the other one goes to the infinite. One of them goes to 1, and the other one goes somewhere else, goes to the place that is in a harmonic relationship where the cross ratio stays the same.
Ah.
So the cross ratio between these 4 points here and these 4 points here are the same, even though one of them's at the infinite, one of them's at 0, one of them's at 1, and one of them is somewhere else.
How do you establish the cross ratio between 4 points? The cross ratio as originally defined involves 8 points.
8 points.
A, B, C, D, and A prime, B prime, C prime, D prime.
Well, 1, 2, 3, 4, 1, 2, 3, 4. So those are the 8 points.
But they're not on the same sphere.
Of course not. Neither was the other one on the same line. A, B, C, D is on one line, and they're projected onto another one.
Nevertheless, there was a projection.
Yeah, and this is a projection. This is a projection of this sphere onto that sphere.
This projected onto the
What is the method of projection?
These are all, every point on this sphere is a complex number, and this is the function. A, B, and C, A, B, C, and D are the 4 points. There's a typo here. This should be a D. And so it just transforms it to that one. It's just a complex mapping.
Still, I mean, still not. Somebody asked me, please show us how each point on the first sphere is mapped onto the second.
Right. You take every point on this sphere, Z, and you put it into this equation where A, C, and B are the red.
Green.
No, the red, black, and light blue numbers. Okay? So those are your constants. Z is your variable. So you take every point on this sphere and you put it into this function, and it will map, it'll turn it into that sphere.
You can also think of it as
Yeah, go ahead.
you can think of it as something related to a phenomenon, like, for example, the thing that comes to my mind is light. I mean, everything you talk about would be the sun
Yeah.
and everything else. And the sun is about the same exact theory
Fermat.
as Fermat, yeah, right. And Huygens with the refraction. And all of this stuff, if you think of it
Absolutely.
associated with what we did with the refraction, showing that you can't use algebraic
Right.
you can't use algebraic relations to understand why the light beam ends up where it does,
Mhm.
because of another factor, which is least time.
Mhm.
So if you think of this as being like an
Yeah.
exemplification of that kind of principle, and
Exactly.
you may not think that the beginning of light.
No, it is that
because
principle,
there's always
but
a beginning and an end to light. I mean, light
Right.
works in this kind of
but
way.
instead of projecting it instead of thinking of the light as projecting like onto a shadow where you see the object in the shadow,
Right.
now you're projecting all of the universe into another state of the universe.
Yeah.
In other words, so things are changing. But what is okay? So what you see here is that you end up with. But here's the point, right? Aside from the function, what you see is that you get these variations. There are 6 different variations among these among this transformation, which preserve the cross ratio, and those are these 6. That's one of them, which is just to invert it, right? What is it? It's a physical constant. And the same reason why, and the same reason why
Just 5 platonic solids.
there are 5 platonic solids. Why 5?
6 transformation, no, it means you have
The universe won't permit 6.
Okay.
6.
Finish your 6
Okay.
discussions.
All right. So one is you just invert it, right? So you see between the black goes and the red change their place, the blue stays the same, and the green inverts so that it stays in the same. The cross ratio is preserved. Okay. The other is to do that. Okay.
What?
1 minus W. All right. So so the effect of that is to move 1 is to interchange 1 and 0. Okay. But the black stays at the infinite. Okay. The other is this one.
The first is a whole cycle.
Yeah.
You're comparing the whole.
The whole thing.
Instead of comparing BD to AD, you're comparing one cycle to a part of.
No,
No,
I'm
no,
doing.
I'm not-
No.
Okay.
Okay. It's like it's like a modular function. It is a modular function. Okay. So this is the other transformation, which puts the blue at 0, the red at the infinite, the black at 1, and it puts the green where it has to be to preserve the cross ratio.
Huh.
And then this one, 1 over 1 minus w, is another variation.
What was the one before that?
W minus 1 over w.
Okay.
And the sixth one is w over w minus 1. Now those are the same 6 permutations of the cross ratio. This is an ancient, this goes back to Descartes. These are the same 6 different possible, if you have 4 numbers and you take them in any order, there are 24 possible ways you can order them, and 6 of them, all of them, only 6 of them will be different, right? Okay, and then they're all put together.
That's what Moira said. He said all this probability stuff is only gambling.
All right. Now, now here's the same thing in a different way. Those, what Gauss figured out was those were special cases of a type of motion which are the so-called rigid motions of the sphere. That is, the complex transformations which just which rotate a sphere so that all the internal relations stay the same. Okay. Whereas, just if you look at, just to give you an example, what is a non-rigid motion of the sphere? This is a non-rigid motion of the sphere because you.
What is?
Well, where I have a sphere, John, where all the which is just a sphere where you have your lines of longitude and latitude, okay, and the lines of latitude get closer and closer to each other as they go up, and then its transformation jumbles everything up, okay, whereas a rigid motion is one that just rotates the sphere. And it doesn't change the internal relationships of the sphere, which is, for example, what the 5 regular solids are. They're basically rigid motions of the sphere. Take the octahedron, is a rigid motion of the sphere by the 3 possible ways that you can rotate the sphere 90 degrees. There are only 3 possible ways to rotate the sphere 90 degrees. One is this, and then if you do it again, you're back to the same place, right? The other is this. So there are only 3 ways to rotate the sphere 90 degrees.
Rotate
Around the center.
rotate around the, okay, you take the axis rotation, take the south pole,
Yeah.
rotate around that axis magnetic. And another is to rotate the North Pole down to the equator along, say, the 0 meridian.
Yeah.
And another is to rotate the North Pole down to the equator along the 90th meridian.
Right. That's okay. So that's an example of a rigid rotation. All right, and here's so those were a special type of rotation. All right, which you can see here. I'll just go through it, right? So one is, what you do is you create certain cycles. Just like the polygons are a cycle, right? Gauss's division of the circle. You have, the famous thing where you have our circle, right? And you can connect every point. You can connect every other point. You connect every 3rd point, and you get the same thing in the opposite direction. You connect every 4th point, you get the same thing, and you can connect every 5th point. And that's basically it. You got 5 and only 5 possible types of cycles there.
Right.
Okay? So this is a type of cycle in which, I'll show you, you get a cycle, but it closes after 6. So you do this action. Well, actually, I'm showing you this is something different. These are the different types of motions that you can do to a sphere. One is complex transformations. Yeah. all right, I'll stop with this. So you have one is just a rotation. Okay? The other is something like this, in which you can see what we're doing here by looking at what happens to these dots in this. The dots all move down like that, right? And you can see that these circles here scrunch in, right? So that's a non-rigid rotation. This is a rigid one where we just rotate everything. This is rotating around the axis between the axis that goes this way, right?
And the one you showed before, you're showing the change both in that plane surface and in the
So now what's happening is everything is scrunching down towards the pole, right? So you see it gets out of shape.
All those circles around it are spreading apart.
Yeah, are spreading apart at the top and scrunching up towards the bottom, right? And here it's going the other direction. Now it's scrunching
It's
up.
like when you did the thing where you took the center of the circle. and
Yeah.
you put it out.
Yeah, right. And here's one where it rotates in a different way. So those are the now. But here's a rigid motion. But nobody's going to understand this unless I stop now and pick this up next week.
Yeah, there's the 6.
There's-
You gotta be flexible.
yeah, what can I say?